Hello everyone, myself Rekha Sharma, bearing roll number 21NS0161, and I am presenting a presentation on the topic STM, that is scanning tunneling microscope. Now today we are discussing about general component of STM, tunneling current, feedback system, tips and brief overview of STM. Now first discuss about what is STM, that is the scanning tunneling microscope. The scanning tunneling microscope was developed by Gerd Beining and Heinrich Rohrer at IBM. When a metal tip is brought near a conducting surface, electrons can tunnel from the tip of the surface or vice versa. Because the tunneling probability is exponentially depends on the distance, the contours of the surface can be mapped out by keeping the current constant and measuring the height of the tip. In this way, atomic resolutions can be obtained. For this work, Beining and Rohrer shared the Nobel Prize in 1986. Now discuss about the basic component of STM. There are 5 basic components: metal tip, piezoelectric scanner, current amplifier, that is NA, bipotentiostat, BIAS, feedback loop or current, turning current from tip of the sample or vice versa depending on bias. Current is exponentially depends on distance. Rheostat scanning gives two-dimensional images. Feedback is normally based on constant current, thus measuring the height of the surface. Now, this is the figure of basic component of STM. This is tunneling current amplifier. This is control voltage or piezo tube. This is distance controlling and the scanning unit. This is turning voltage. This is the tube. This is the tip. Now this is the fundamental figure of STM. Brief history of STM. The first member of SPM family, scanning tunneling microscope, STM, was developed in 1982 by Gerd Beining and Heinrich Rohrer at IBM. In John Rich created the idea of STM. Both of the two people won Nobel Prize in 1986. Now we are discussing about STM tips. STM tip should be conducting metal like platinum. STM plays with the very top outermost atom at the tip and the nearest atom on sample. So the whole tips is not necessarily very sharp in shape, different from the case of AFM where contact is necessary and crucial for feedback. Now, how do we obtain these wonderful tunneling tips where only one atom at the top? Really easy to obtain such tips simply by cutting a thin metal wire using a wire cutter. There is always a single atom left over the very top. Tunneling current or result of overlap of tip and simple electron wave function. This wave function is phi. There are two requirements. One is simple distance electron wave function. This wave function is phi. I already told you, overlap, and two is bias for net current flow. Now, energy density of states Fermi label. This is the Fermi label denoted by epsilon F. This is the energy. This smiley was nothing but this smiley is electron. This smiley are the electrons. Now this is a sample. This is electron. This Fermi is the label. The density of a state at energy, that is epsilon. Does epsilon is the number of electron. This is electron sitting in the strip divided by delta epsilon. Electron density of the state Fermi label. The electron fill up the energy valley in a sample until there are no more electrons. The top energy level which electrons sit is called Fermi level, that is EF. For every energy, every energy E, this E is the energy, the density of state is the number of electrons sitting within del E. That is, this is not D, that is del E of electron divided by del E. So, for the energy down above as a blue strip, that is delta E is approximately 7 by delta E. Now, tips and sample lined up exactly under zero bias. This is energy denoted by epsilon. This is work function. I already told you work function is denoted by this phi. This is the symbol. This is a vacuum barrier. This is a Fermi label. This imaginary line is called Fermi label. This is the tip. This is the tip. This is the sample. The electron in the tip and the sample are sitting in two separate valleys separated by a hill which is a vacuum barrier. These two tips and sample are separated by a vacuum barrier. Potential, their Fermi label lines up exactly. There are no empty states on either side available for tunneling into. This is why we apply a bias voltage between the tip and the sample. Tunneling current at bias. This is the energy denoted by epsilon. This is the sample, that is electron volt, and this is the sample. This smiley is nothing but this is the electron. Now this is a vacuum. This gap between the sample and tip is bias voltage, that is electron volt. This is the tunneling electron. This electron is tunneling electron. This is the tips. Now, by applying a bias voltage to the sample with respect to the tip, we effectively raise the Fermi level of the sample with respect to the tip. Now, we have empty states available for tunneling into. This is the graph. This is a vertical line. This is y-axis. This vertical line is y-axis. That is current. Current is denoted by I. And this vertical, this horizontal, that is x-axis. This is the distance. It obeys the Ohm's law. This is the graph. Now this phi is work function or energy barrier. This E means the electron charge. The charge of the electron is denoted by E. M, the electron mass. H, the Planck's constant. V, applied voltage. V is the applied voltage, and D means tip sample distance. D is the distance between tip and sample. Now, there are some common metals. The work function of common metals. There are this is the metals. This is silver, aluminum, gold, cesium, copper, lithium, lead, tin, chromium. These all are the metals, and this is the work function. Work function is denoted by phi, and SI unit is electron volt. Now this is the STM constant current mode. Since STM images the outermost atom on sample surface, USB is normally required to assure no surface, example, coverage of air molecules or water. So, as the image single atom or at atomic resolution. This black and blue is upper layer, and this only blue is lower layer. Now, this is the constant current. This is the constant current mode of STM, and similarly one can have the constant height mode using the same feedback system. The tip is scanned by a line above the sample surface followed by topography of the sample. So this is all about my topic, that is scanning tunneling microscope. Thank you.